Welcome to our soil testing video series, jointly presented by the Geotechnical Division of the HKIE and the Geotechnical Engineering Office of the CEDD. The production of this series is made possible by the generous support of our sponsors. In this video, we will cover the Atterberg limits. Atterberg limits are simple yet very useful measurements for fine-grained cohesive soils. Let us start this video by imagining you're in a pottery workshop. If I ask you to start molding a clay vase, you will probably add some water to your dry clay as the first step. Adding water seemingly affects the clay's consistency, allowing us to mold the vase with greater ease. But we must be careful not to overdo it. Too much water and our vase will collapse or even turn into flowing mud. In soil mechanics, moisture content is defined as the ratio of the mass of water to the mass of the soil grains. The minimum moisture content at which the clay becomes plastic, when we can start molding the clay without it crumbling, is called the plastic limit. The maximum moisture content within plastic state at which the clay starts behaving like a flowing mud or a liquid is known as the liquid limit. The plastic limit and the liquid limit are known as the Atterberg limits. The difference between the two Atterberg limits is known as the plasticity index. A soil with a moisture content within the plasticity index is said to be in a plastic state. Soils with a large plasticity index behave like sponges and possess a high capacity to retain water compared to soils with a small plasticity index. The table here shows typical ranges for Atterberg limits of some clay minerals and soils commonly encountered in Hong Kong. Something important to emphasize here is that the Atterberg limits are only relevant to fine-grained soils. If the soil is dominated by coarse-grained particles, you may still obtain the Atterberg limits of the fine portion of the soil. But these Atterberg limits would not tell us much about the soil as a whole. As one can imagine, the moisture content would have a significant impact on the shear strength of a fine-grained soil. The undrained shear strength at liquid limit and at plastic limit typically has the order of magnitude as shown here. But just knowing the moisture content isn't enough to gauge how plastic or liquid a sample of soil is. Simply put, we don't know the wetness of the soil simply from moisture content alone. Noting that the undrained shear strength of a cohesive soil depends critically on its wetness. We need something better to assess how close we are to the plastic limit and the liquid limit. Here, geotechnical engineers like to use something called the liquidity index, which is defined by the equation shown here. This equation will roughly give us a value between 0 and 1. The wetness of our soil increases as the liquidity index approaches 1. Note that two soils with a similar moisture content could have very different liquidity indexes. As shown here, soil 1 is very wet while soil 2 is pretty dry. Okay, let's now talk about how we can determine the Atterberg limits in a laboratory. In Hong Kong, test method 6.1 of GeoSpec 3 specifies how the liquid limit, plastic limit, and plasticity index are to be determined in a laboratory. And test method 6.2 specifies how the liquidity index is calculated. It is important to note that these tests are only performed on soil specimens containing soil particles completely passing through the 425 micron sieve. A cone penetrometer is used for determining the liquid limit. In this test, we let an 80-gram stainless steel cone penetrate into the soil specimen by its own weight and measure the depth of penetration. The moisture content of the soil is also determined. At least 3 more specimens with different moisture contents are prepared, and a penetration test we have just described is then repeated. A graph of penetration against moisture content can be plotted. The moisture content corresponding to the penetration of 20 mm is taken as the liquid limit of the soil. Plastic limits is determined using the hand rolling technique. We first shape the soil specimen into a ball. Then, we mold a small portion of the soil to form a thread of about 6 mm diameter. Lastly, we roll our soil specimen into a thin 3 mm diameter thread. We then pick up the threads and repeat the last step. which is rolling the soil specimen into a 3 mm diameter thread until transverse and longitudinal cracks appear on the soil thread. The moisture content of the soil at this stage is measured. The test is repeated for another specimen. If the two results differ by more than 0.5% moisture content, repeat the whole test. Otherwise, the average of the two measurements is taken as the plastic limit of the soil. We have briefly discussed what Atterberg limits are and how they are determined in a laboratory. But some questions still remain. Why do we care about them? Why do engineers want to know them in the first place? There are several useful soil properties that can be assessed using the soil's Atterberg limits. Firstly, by knowing plasticity index and liquid limit, we can use a plasticity chart to classify a soil sample into organic or inorganic silt or a clay with different degrees of plasticity. Secondly, we can estimate the sample's compressibility in terms of compression index using the liquid limit or plasticity index. The compressibility of a clay in general increases with increasing liquid limit or plasticity index. Furthermore, we can use the Atterberg limits to estimate a fine-grained soil's shear strength. The plasticity index can be used to estimate a clay's angle of shearing resistance. The angle of shearing resistance decreases with an increasing plasticity index. The liquidity index can be used to estimate the undrained shear strength of a fine-grained soil. The undrained shear strength decreases with an increasing liquidity index. Moreover, we can use the plastic limit and plasticity index to assess a soil's principal clay mineralogy such as kaolin, aelite, and montmorillonite. For example, a soil has a plastic limit and plasticity index values as shown may probably have kaolin as its major constituent. There are often contractually binding material specifications that put boundaries on the Atterberg limits. For example, the HKSAR government's general specification for civil engineering works contains requirements on the liquid limit and plasticity index for special field as shown here. Hence, an engineer should be equipped with the relevant knowledge to comply with such requirements. We have explained before that Atterberg limits can be correlated with some soil parameters related to compressibility, strength, mineralogy, etc. This provides the engineer with a way to compare these parameters with those obtained from other more sophisticated tests such as the triaxial test and the odometer test. By doing so, the engineer may gain some insights about the consistency of the test results. This wraps up our video on the methods for determining the Atterberg limits of soils. We hope you have gained valuable insights on the theories, procedures, and applications of these tests. Join us in the next video as we explore another exciting topic in soil testing. Thank you for watching.